Our work is about multiple tracking with focus on indoor soccer player. I am Erickson, and in our context, collective sport is, as indoor soccer has been scientific interest applied to tactical analysis and physiological analysis. These analyses are all the time based on trajectories of the players on the game. Find these trajectories is a difficult work, mainly if it is you manually marked with specialized work. So using computer vision methods, we can help it to find the trajectories using, in our case, automatic detections, multiple cameras, data fusion, and tracking. So our objective are find the trajectories of indoor soccer players with minimal human interventions. Our input are a game recorded using multiple cameras and a court map with characteristics points to make calibration. So our problems are divided in three main parts. One for multiple camera detections, other for data fusion, and finally tracking. In our approach, we organize the method in four main parts. This one for multiple camera detection, this one for fusion and make a multimodal function to represent the statistical occupation of the court plane. Other one for tracking, and here an appearance model for extracting the observation function. The first part, we use multiple camera detections and the data fusion. Players detected use Viola and John method to find players. It's a classical method on computer vision. And we use the middle of bases of rectangles as players' foot, like here. The Viola-Jones detections make us a set of rectangles on image plane. And we need an information to project this in a virtual plane, like here. These points representing the player's foot are projected on a virtual plane representing the court plane. And remember, we have a map of this plane with a lot of characteristic points to initializing a homography matrix in each process. So we have 4 cameras and the 4 detectors. Each one generates a set of points, and these points are projected on the virtual plane, and this introduces a noise of position of players in the real world. So we train parameters for each cameras to replace each point projected here with a Gaussian function with no parameters. So this set of Gaussians are fused with a mixture of Gaussians with the same width here, and we have a multimodal function to represent the coach occupation in this frame. In second part, we have a particle filter here that use this multimodal function as observation process. Particle filter can be represented fast with this figure. In step 1, we have a set of particles represented by circles, and width are represented by size of circles. In second one, we have another set of particles done by sampling the last set here, by sampling the particles with repetitions and priorities for biggest width. In the third step, we make propagation. We introduce a small part of movement to make predictions, and introduce a little noise to make these particles different. So in 4, we have the observation function. In our cases, we use the multimodal functions to make observation here, and then we have a new set of particles with good widths. We use one tracking for each player, and the position of players are computed with the weighted average of particles, like here. So we have a lot of situations, a lot of bad situations like this. These observation functions can't resolve the situation because all Gaussians in the mixture have the same width. So it's a bad situation for us. For this, we introduce an appearance model to strengthen this observation and make make it better width in observation functions. Our appearance model have a set of histograms here, and we use a detected sub-image here. And these images are divided in 3 parts, top, middle, and bottom. And then each one generates a set of histograms, H, S, and V for this space of color, and one for gradient, and the other for angles of gradients. So we're measuring a similarity between 2 appearances using correlation of product of correlation of correspondence histogram in 2 appearances. It is necessary to represent a player's appearance in the time because we track in a longer period of time. We use a historical of good appearances. We need to get the similarities of appearance and this historical. For this, in fact, we compare detected appearance with all appearance in that historical model. And then we get the biggest one and represent by letter P. With this, we can rewrite the multimodal function using width with 2 different Gaussian. Now we have, in this situation, different width using multimodal functions and appearance model. In this situation, different people have different widths. The historical appearance need to be dynamical and updated. For this, we replace candidate to out for candidate to in. The last used appearance in the model is a candidate to out. And the appearance that generates the best similarity using this model is a candidate to in, looking for a threshold. For cameras, recording each game with some intersections, and we have 7 games. We consider each playtime with a game, so we have 14 games recorded by 4 cameras. 1 tracking for each player and 2 refers to be tracked. We have 2 training phases, one for detectors and the other for parameters of Gaussian in the multimodal function. To detectors, we use about 16,000 positive examples and about 18,000 background examples. To calibrating multimodal function parameters, we use detections projected on the court plane and compared this with manual markings. These correspondences are found by shorter distance. We found mean and the errors of these correspondences to make parameters and then use this to make Gaussians in the multimodal functions. Proximity of players causes many untracked situations when without to use appearance model. But in this case, looking for success case, most mean errors are below 1 meter. In the best case, we have 40 centimeters, and in global cases, 73 meters, like in this table. This is the worst one. This is the best one. And here is the global measurement. So without appearance model, untracked situations, sometimes intersections trajectories are unsolved because without appearance model, all the Gaussian in the mixture have the same width, and observation function for the particle filter is not so good in these situations. Trajectories that are coincident for a moment tend to be fused because it's very difficult to separate, like in celebrations moments. It's very difficult for us, and it's very common in this problem. So, with appearance model, particle field observations are strengthened by appearance model, and the result is more better. There are still unsolved situations, like celebrations moments. Looking for a success case, we can see that here that we have a little more bad results. Worst case, we have 81 centimeters, like this in this table. Here the best one is the worst one, and the global results. Comparing two, we can see that this is better result. We present a method for recovery trajectories of indoor soccer players. The observation function uses multimodal functions with an appearance model. And the main advantage of our method is the automation, and we have human intervention just in initialization. The main disadvantage is the celebration moments are unsolved. This making method not able to track complete trajectories. As a future work, we intend to focus on the problem of celebration to find a method that can deal with this difficult problem. Our acknowledgements. Thanks for all.
Okay, so we're now open for questions. Come on, I cannot ask questions.
There are a lot of other approaches. Didn't you go through them, and didn't you try to compare? I think it is a well-known and well-worked problem in the literature.
We are still working in this project. So in this case, we don't compare. But we know that another works. We have one to compare used in real world at the Unicamp by a equipe of physical education specialized people in physical education working with this kind of problem. So that work is that method is very difficult to use because that method is make it, I don't know, to other kind of soccer, outdoor soccer. So that problem is a little different. And using this method for indoor soccer player, we have a little of differences and a little of difficulty to use that method because this we don't compare with this.
Just a simple question. You mentioned that at the initialization, the user must initialize the tracker. How this is done?
Now it is manually. We have a step. Click. Yes, using mouse. Now we have initialize step to using mouse to initialize tracked and to initialize homography metrics.
I would like to know if you tried to use a people detector maybe for disambiguate the situation where there is two people around in celebration or something like this, or it's just only that you understand that there is something in the problem you showed at the end. You say that in this situation where many players are not moving, and especially are players with the same dress, so are not easy to recognize by the aspect. You just only, it's very normal that you cannot find a solution, so don't have problem about this. But I would like to know if you tried to use people detector or something like this in order at least to understand that there are 2 or 3 people and to reinitialize the system as soon as one is moving. I know that many work, for instance, the work of Andrea Cavallaro that is working of basket indoor, but similar problem, is doing in university in UK, is doing similar things. So I don't know if you try to use people detector to understand how many people are in the area where you don't find a situation.
Yes, the difficulty in this case is really separate the people involved in that situations. So to tracking, I need to separate and tracking the same people all the time. It's very difficult. So in the finish of this moment of celebration, we have people detection and detect the players again. But the problem is continue tracking the same people.
Let me clarify the question. The tracking we're doing is statistical tracking. The observation is a people detector, so we're already using the people detector to create observation. So, you know, like, so.
The people is one or the other one in order to
I
create
see, like
a more
part-based
precise,
model.
yes,
Yeah,
like the one of Frenzenwald or something like this part.
That's part of his future work to try different type of detectors and stuff.
Okay, thank you very much.